In this Cloud RF tutorial, we're going to cover calibration. To improve modelling accuracy, you need to calibrate using real measurements. This tutorial will cover importing this data into Cloud RF and how to fine-tune your model to get accurate results. I'm now going to go over the process of preparing my data for import into Cloud RF. For this tutorial, I'm using survey data from Southampton in the UK. We're going to remove weaker measurements below -100 decibel milliwatts, which are more likely to be reflections or noise. With my reduced dataset and it being laid out in the correct format, my data is now ready to be imported. Before importing my survey results, I'm going to update the interface with the parameters for my transmitter and receiver. When doing a calibration, we need to make sure we have an appropriate colour schema selected. You can only calibrate your model to the accuracy of your colour schema. Choosing a scheme such as LTE with 5 dBm steps would impact the calibration significantly. We'd recommend using the default Calib schema or a custom schema with 1 dBm steps for performing the calibration of the model. By carrying out a calculation at this stage, I'll also be able to get a good baseline of my current settings for my model environment against survey data. To import survey data into the interface, press the Import button on the bottom ribbon. Select Calibration, then choose the file you want to upload. I can now see that my survey data is valid, with 4,826 valid points being found. I can press OK to show the survey data on the map. We can now see these points on the map, as well as calibration metrics in the bottom left corner. This is a live updating metrics report, which gives you details about the computed error. A good error value is less than 8 decibels, and an excellent value is less than 5 decibels. Anything greater than 8 decibels normally requires adjustments to your modelling parameters. Be aware that field measurements contain receiver error. This can vary from 1 decibel for a high-quality receiver to 3 decibels for a cell phone. This inherent error is separate to modelling error, so if you achieve 9 decibels alignment with a cell phone, your model can be deemed correct. To calibrate the model, we first of all need to make sure that all the points in our survey are covered by the range. This can be done by zooming out and panning, and then using the Path Profile tool to work out the distance of any points that aren't included in our current cover. From my survey data, I can see that I need to extend my range to at least 14 kilometers. By ensuring that all the points of our survey data are covered by the radius of our calculation, we can quickly make some improvements to our calibration. The radius of a calculation can be altered in the output menu. By running another calculation with this increased radius, we can now see that our model is becoming more calibrated to our survey data. The next step to consider is changing the model used for our calculation. Currently, I'm using the ITM Longley Rice model, but I can improve my calibration by altering it. Due to the mast being 17 meters tall, a cell site model may be more appropriate, such as the Okamura POS 231 or the Ericsson model. I am now going to perform calculations with each of these models to work out the best one suited for my calibration settings. Having identified the Ericsson model being the most suitable for this calibration, I can now begin to explore the other settings within my model. By looking at points of the map, as well as our coverage metrics, we can see that we still need to do some work on our model. Within Cloud RF, there are multiple environment options. These include using either the standard or custom clutter profiles, using either DTM or DSM elevation, as well as being able to toggle land cover and buildings on and off. To view a clutter profile settings, press the green button in the environment window. Within this window, we can create, manage and delete clutter profiles, as well as setting the attenuation profiles for various obstacles on the map. All of these variables can be changed to suit the environment that you're operating in, be that the average height of trees in the area, the thickness of walls used by buildings, as well as the option to create custom obstacles. These variables can be changed and saved to an existing profile, or a new clutter profile can be created by using the options in the upper right hand side of the window. Having saved a custom clutter profile for this model, I can now select it within the interface for calculations. Although the accuracy of my model has decreased in this first calculation, I can now use the Path Profile tool to work out how to improve my clutter profile to increase accuracy. By using the Path Profile tool, I can select a point to see the path profile analysis of my signal to reach that location. This also identifies which obstacles interfere with the signal, in this case, trees and buildings. I can now increase or decrease these variables within the clutter profile to make it fit the environment that I'm modelling. These variables can continue to be changed until they accurately represent the area you are modelling. After creating a clutter profile for my environment, I can now fine-tune my model to get accurate results. The reliability of the model is currently set at 50%, which is optimistic. I can make the model more conservative to a level which matches the survey data I've collected. These settings can continue to be adjusted until the model is fully calibrated. With reliability set at 70%, I now have an optimum score for my calibration at 7.9 decibels. CloudRF also supports the use of LiDAR data, which is more accurate than DTM. With a good score for my calibration, I can now cross-examine the model against specific points on the map. If you'd like to know more about calibration, please see the link below to our documentation. To keep up to date with videos showcasing our new features, please subscribe to this channel.